So thank you very much and welcome to this last session of IMAV 2021. So for this session, we have 3 papers. The first one is the paper number 5, Indoor Visual Semantic SLAM Improve Bio and RGBD for Narrow Space Navigation. So I wonder if the author of this paper is here. I don't know. Paper number 5, Indoor Visual Semantic SLAM.
We changed paper 5 and paper 6, so
yes, they change, Fermi. So yes, paper 6 now. Please go ahead.
Okay, no problem. So thank you to be here. So okay, you have 50 minutes, Miguel. Yes.
Yes.
Okay.
So I will.
Please, you have the floor.
Okay, so I'm Miguel Fernández Cortidas. I'm from the Computer Vision and Aerial Robotic Group of the Universidad Politécnica de Madrid, and I will present our paper, which is called A Framework and Evaluation Methodology for Autonomous Drone Racing. So I will put the video that we have made for this presentation.
The sound is very low.
The audio can be. Can you hear the audio?
No.
Okay, so.
I can hear. We can hear the audio.
I don't know why.
Maybe in the setting. The audio setting.
When you share the video, you have to make sure that you press the option of using sound. So
okay,
when you click share screen at the bottom of the next.
Okay.
Click on that.
In this video, we present a novel framework and evaluation methodology for autonomous drone racing. In recent years, autonomous drones have been increasing their application in different tasks like firefighting, search and rescue, or inspection in dangerous environments, such as tunnels or caves, or even erupting volcanoes. Their maneuverability and capability to access hazardous locations without endangering human lives make them ideal for these tasks. However, the short time flight of these aircraft greatly limits their use in long-duration tasks. To take advantage of this, it is interesting to develop agile drones that can explore or traverse an area in short time. Autonomous drone racing is a great environment to push agile drones to the limit. The high speed and agile maneuvers required for this purpose increase the difficulties of locating, controlling, and generating trajectories. In recent years, autonomous drone racing competitions like IRO's ADR competition or the more recent Alpha Pilot have helped to improve the state-of-the-art substantially. However, autonomous racing drones are still far from reaching human pilot performance, and a lot of research has to be done to accomplish that. To test different techniques to get the best results, it is useful to work in a modulated environment that allows you to develop and validate different algorithms independently. In this work, a complete architecture system and an evaluation method for autonomous drone racing research is proposed. The system architecture that is presented in this work has been developed using the Aerostack framework, an open-source multi-purpose software framework from the development of autonomous multi-robot unmanned aerial system, created by the Computer and Aerial Robotics Group. The framework architecture is organized in the following layers. On the right, we can see the sensor-actuated interface layer, which is in charge of receiving data from sensor on the aerial platform and sending commands to robot actuators. Data provided by the simulator are included in this layer too. Next to this layer, the communication layer can be found. Our architecture uses this common communication layer that contains shared dynamic information between processes. This channel facilitates process interoperability and helps to reuse components across different types of aerial platforms. The following layer corresponds with the robot behavior layer, in which the robot functional capabilities, including motion control, feature structure, state estimation, and navigation, are implemented. Finally, the control layer executes a mission plan specified in a formal description. A behavior coordinated component is used to translate planned tasks into consistent activation of robot behaviors. The following is a more detailed description of the robot processes developed. All the set of behaviors that are responsible for controlling the movement of the drone are included in the motion control layer. This category includes simple behaviors such as takeoff, hovering, or landing, as well as more complex behaviors such as generating a trajectory and making the drone follow it. In order to realize aggressive maneuvers on a quadrotor, it is necessary to employ a non-linearized controller. We have implemented a quadrotor control algorithm based on differential flatness, inspired by the work made by Mellinger et al., with several modifications, so the output of the controller corresponds with angular velocity reference and the desired collective thrust of all motors. The input of this controller consists in the position, speed, and acceleration references provided by the trajectory generator. Due to the need of generating trajectories for the controller, a polynomial trajectory generation has been used. The trajectories are generated on a set of waypoints and are optimal in accelerations, which guarantees smoothness in the actuator commands. In order to achieve the level of control required, it is necessary to provide the best state estimation possible to all components involved. Aerostack Frameworks already provides multiple components for this task, obtaining data for multiple sensors such as cameras, for relative positioning to a certain object, IMU, laser sensor, depth cameras, or LiDAR. However, for the real flights, we decided to use the state estimation provided by an Intel RealSense T265 tracking module due to the ease of use and the reduction of the computational load of the onboard computer. Moreover, support to motion capture systems like OptiTrack is also integrated. Perception is a key problem in the proposed scenario, since UAVs need to detect and locate each of the gates accurately to be able to complete the full track. Since the detection and post-estimation of the gates is a difficult problem itself, to evaluate the rate of the proposed framework components without the influence of possible errors in perception, we place Aruco fiducial markers in each gate to estimate the relative position of the UAV's main camera. Each marker also encodes a unique gate ID, enabling us to design arbitrarily complex tracks. When the gates are located in the real world, it is necessary to plan the path that the aircraft must follow to pass through them and avoid other obstacles. For this approach, we consider two scenarios. In the first one, lack of knowledge of gate position is considered. The aircraft does not have any information about where the gates are located, so it has to begin looking for them in order to generate the waypoints to pass through the gates. As long as the aircraft passes through the circuit, new gates will be in sight, so the quadrotor can add these gates to its route. In this scenario, the aircraft is always considered to see at least the following gate. On the other scenario, we consider gate position awareness. The aircraft knows an approximate position of each gate of the circuit, so it can generate complete trajectories through all the circuit that must be corrected with as long as the gates are in sight. So it has to update the initial gate positions to pass through the circuit. This is how the majority of the autonomous drone racing competitions work. In both approaches, each gate center is treated like a waypoint in the path, and this waypoint position is updated as the quadrotor flies through the circuit. Whenever the quadrotor passes through one gate, this gate center is removed from the path. The following are the different experiments that have been carried out to validate the performance of the proposed framework. First of all, Simulation experiments were done trying to accomplish a 5-gate circuit using the state estimation provided by the simulator. Then, two types of experiments were performed in a real environment. The first consisted of passing through a single door at different speed. In the second one, the objective is to go through a small circuit of 4 gates. In both experiments, the state estimation provided by the Intel sensor is used. However, in the first experiment, the motion capture system will be used to measure the error made by this sensor. To measure the performance of the system architecture proposed and the switchability of the different algorithms selected, several metrics have been used. For measuring the accuracy of the state estimation algorithm, we compute the root mean square error between the estimate state and the ground truth. To evaluate the performance of the controller, we decide to measure the trajectory following error, calculate with the root mean square error between the trajectory sent by the trajectory generator and the real trajectory followed by the aircraft. In autonomous racing, other metrics like the maximum speed reached, the medium speed, or the elapsed time to go through all the circuit must be taken into consideration. All metrics obtained from the different experiments were obtained automatically using an evaluation script on the raw data recording during the flights. We use Gazebo Simulator for the simulation experiments. Here, a video of the system working can be seen. In the bottom right, a first-person view of the aircraft is shown, while in the left part, the data acquired during the flight are plotted. In green, we can see the trajectory generated, and we can observe how it changes when the estimation of the gate position is updated. The aerial platform used for the real experiments was a custom quadrotor, based on the DJI F330 frame. This platform was equipped with a Pixel 4 Mini as the aircraft autopilot, an Intel RealSense T265 tracking module used for state estimation, and an USB fisheye camera for the gate detection. Additionally, the aerial platform was equipped with a single board computer NVIDIA Jetson Xavier NX for onboard computing. All computation required for the real experiment occurred in this single board computing. In order to obtain the ground truth position of the aircraft during some experiments, a motion capture system was used. For localizing the aircraft inside the motion capture system area, several IR markers have been attached to the platform. Here, we can see the real flight experiment trying to pass through 4 gates. In the video, a security pilot follows the drone, but it does not take the drone control at any moment. As we could see, on the simulated flight, the system was able to complete the whole circuit at different speeds, reaching speeds up to 3.2 meters per second, with the trajectory following average error around 50 centimeters, which validates the basic operation of the system. To sum up, in this work, a modular framework for autonomous drone racing has been proposed and validated through several experiments, not only on simulation, but also on real environments. being able to fly up to 4.16 meters per second, and to go through a small circuit successfully using onboard computation. The state-of-the-art algorithms proposed for each module, combined with the evaluation metrics proposed, constitute a baseline for research on improving autonomous agile drone flying. To improve this framework, a wider range of possibilities to choose for each module must be given, like adding model predictive controllers, learning-based gate estimation methods, or a visual inertial odometry estimator fused with other sensors to improve the state estimation. Moreover, the domain gap between simulation and real life is substantial when non-photorealistic simulators are used. Using a simulator like Flightner or FlightGoogle's will help to develop and test algorithms that rely on images taken through the flight. Thanks for watching.
Okay, thank you, Miguel, for this interesting presentation. It's impressive what you do. So maybe we have time for some questions. I don't know if the audience has any questions. In the meantime, I have one question, Miguel. From your point of view, what is the challenge to design algorithms for racing? For example, control algorithms or state estimation. What is the more important challenge from your point of view?
Well, one of the most, the challenge most these kind of algorithms are the low, the small time that you have for compute the algorithms, and when you put all the algorithms into an onboard computing, the low capabilities of computing that this computer has compared with a desktop computer, for example, makes you force you to use algorithms which are not as good as you can use if you had more computational power. But having to compute all your algorithms in a small time, because when you fly at high speeds, the reaction time is so slow that you must use as efficient algorithms as you can get. And the same is in control, can be the same problem has to be in control algorithms, but also when you have state estimation algorithms, when you use visual algorithms for localization the drone in an environment. When you go at high speeds, motion blur tends to occur unless you use some even cameras or things like that. And this is challenging too in order to develop autonomous drone racing drones.
Yes, I think it's not easy. It's not easy. In this moment, what kind of control algorithm have you implemented in your drone?
It is in this work we use an adaptation of the differential flatness-based controller that was designed by Vijay Kumar and Mellinger. But we did some small adaptations in order to don't have to measure exactly the dynamic parameters of the drone, and let the autopilot deal with these uncertainties in the model of the quadrotor, and making it more easy to use in other different platforms, or if other researchers want to use in their own drones, in order to facilitate the use of this controller in different platforms.
Okay, so it's very robust.
Yes.
Okay, so thank you, Miguel, for this presentation.
You're welcome.
Okay, so we will continue with the next paper. The next paper is the number 2. I don't know if the other is here. Yes, it's here. Shinji? Shinji, are you here? Okay.
Yeah, I'm here. Can you hear my voice?
Yes, yes, we can hear you.
Okay. And
Can you share your screen, please?
yes, of course. Such topic is decentralized trajectory generation technique for multiple systems. First, I will give the research motivation. Then I will propose the detailed method. Finally, the experimental results will be given. Recently, multi-agent systems receive many attention due to many such as cooperative surveillance, cooperative strategy, cooperative pursuit invention problem. It requires to generate safe, dynamic visibility trajectories in short time given the environment. However, it is challenging to satisfy all the requirements. There are many researches about the multi-agent motion planning problem. One popular approach is centralized optimization method. It can generate optimal trajectories without deadlock, but it requires time to generate these trajectories, especially for large teams, and it may have high time consumption, may fail due to optimization failure. Another method is centralized optimization method. Decentralized planning is receiving much attention due to space scalability. However, such distributed method cannot guarantee the completeness and may get stuck in obstacle-dense environment. In this work, we will focus on decentralized multi-U-boat trajectory generation method. Our goal is to generate smooth, safe, faster trajectories for multiple routers in cluttered environments, given the initial and terminal conditions. We propose a centralized mental-heuristic gradient frame method based on PC. This method has less computational burden in structure-limited trajectories approximated with neural network. It can also have reduced the time consumption of trajectories and avoid deadlock. In our work, the planning problem of each quadruple K is formed as optimization problem. We design the cost function in terms of smoothness, target prediction, and obstacle avoidance. We use the state estimation and prediction method to avoid the dynamic obstacles and use a cost to bootleg to avoid static and non-convex obstacles. The optimization constraints for quadruple K have three terms: model of the quadruple, dynamic limits, and boundary states. This is the overview of our algorithm. Decentralized IMAV-based cooperative strategy. First, we set up the boundary state of this problem. Then, we use pattern swarm optimization, a grid free solver, to select the relative optimal states while minimizing the cost function. The reason why we choose this grid-free method is that the replanning time is more uniform and thus can improve the success rate. For each replanning process, the states of all quadruples are predicted and are considered in their objective function. Relative closest distance between the predictive trajectory of a quadruple and moving obstacles are obtained through the computation. Besides, there is a guided map to avoid deadlock. Finally, after obtaining this relative optimal target state, A series of reference state xk can be generated solving the two-state boundary value problem. The first few states will be given to low-level dynamic controller, thus recomputing the system state and the current state xk can be returned for the next replanning horizon. The first part is the construction of the boundary state constraints parameters using time-optimal trajectory to get smoothness and faster trajectory, and use the controlling control method to get the obstacle-free trajectory. Given the arbitrary initial states and target goal states, time-optimal trajectory can be obtained by choosing minimum, maximum, or zero of the jerk. It is proved that this trajectory is well suited for the dynamic of the real vehicle. Next, we use these DSCPs, boundary state constraints primitives, to train a neural network. We input the relative states to 4-layer fully connected neural network, and the output is trajectory, including 41 states. The table and the figure show the error of the approximation is satisfying our needs. Thus, we can use this pre-trained neural network to save the time consumption. For the convex obstacles, we use a guided map. The map includes cost to goal, cost value to the goal, and the safety value to the closest distance to the obstacles. And after we get in this map, we can use this to get optimal action at each cell. This figure showing the performance of this guided map. If we don't have the map, the purple one may get stuck in this environment. After using this map to predict the information of future states and navigating Corota 5 to choose an optimal action at each state, if it can reach its destination successfully. Next, we will show the results of untypical position swapping. Each Corota must reach its destination while avoiding obstacles like several pillows. In scenario 2, each Corota must reach its destination while guaranteeing the flight safety in the vertical axis. In scenario 3, the Corotas must reach its destination while avoiding deadlock in the non-convex obstacles environment, like this. Next, to validate performance of our method, we make a compare with other recent multi-Corota trajectory planning methods. We assigned a start point of Corota in a 10x10 environment, and the goal points at the opposition to their start positions and shown in the figure. We executed the simulation with 8 agents and measured the success rate by the size of the agent, which means the ratio of the minimum distance to the collision distance. As you can see, the sequential convex programming method may have high optimization failure. On the contrary, our method shows a perfect success rate. The proposed method also have better performance in terms of time per iteration, which means each recurring time. The decentralized method shows good scalability with high number of agents compared with the centralized method. So the computational time will increase by the number of agents in this ICP method. With the same direct limits, we also compare our method with the relative Western polynomial method. The trajectory is shorter without collision in our method, which means the total trajectory exact time is less. Because we use GLT to get time of trajectory for the barometer. So as you can see, given the same environment and the barometer dynamic limits, the total trajectory exact time is longer in RSFC method than ours. To summarize our contribution, our method is a collision deadlock-free trajectory method. It is also a synchronous, decentralized, and scalable scalability method. We can also maintain the relatively less total flight time with higher safety ratio. Thank you for listening.
Thank you, Jinji-Wang, for your presentation. So if you want, you can start your camera, if it's possible. I don't know if the audience has any question for Jinji. No? If not, I have a question. It's very, very interesting, your work. And can you tell us about the experimental platform you are using for your test? What kind of rotors are you using?
Thank you. And the platform we use is Crazyfile. It is a small co-rotor, and you can just send use the Vicon environment to send them the trajectories, and he will this platform will this platform can also be in real time, and you send them trajectories, and the Vicon environment will tell the Crazyfile where their position is, and this corrotors will fly the trajectory you want.
Okay, so the control algorithms are implemented in the onboard quad rotors, or are implemented in the computer and central computer?
So in this work, we implement this, we mainly calculate the trajectories on computer and send the trajectories to the corrotor. So that's maybe the future work we need to implement. We may need to implement this algorithm on the larger corrotor. Maybe the corrotor may have its own computer. So yeah, I think that's the point we need to do a little bit of work.
Okay. So the optimization algorithms and the trajectory generation, it's carried out in the computer, and after they send to H4 rotor. Okay.
Yeah, but this algorithm is a decentralized algorithm. It is not centralized. So we can also, if we have a computer on each Crazyfile, we can also implement this algorithm in real time.
Okay, so I see. If, for example, in your algorithm, it's necessary to communicate between the quad rotors?
I think if we want to implement this in real time or in the correlator must need to share the information of each other, and because they use the other correlators states to predict other correlators state trajectory, and in this way can avoid the dynamic obstacles. Other correlators in this team for each correlator is a dynamic obstacle. Yeah, so if a correlator want to avoid a dynamic obstacle, he must predict its trajectory in the future. So they must need to know the relative position of its dynamic obstacle. So they must share the information of each other.
Okay, I see. So thank you very much. It's very, very interesting to work. And I think it's very important, this algorithm, in order to implement in real time on board, okay? Maybe, as you say, in the future, you can do that. So thank you very much for your presentation.
Thank you.
And congratulations for your work. Okay, so now we have time, but maybe the author of paper number 16, it's here. Maybe we can test your screen, Juan.
Yes. Hi, I'm here.
Juan Manuel. Hello, Juan Manuel.
Hello. I can share my screen.
Yes, you can.
Yeah. I guess, can you see my screen? It's okay, yeah.
It's okay. So just we're waiting a minute.
Yeah, no, well, it's no problem.
Okay, so I think we can go ahead. Okay, so Juan, you have the floor.
Okay, I am ready. Hello, everyone. Well, my name is Juan Manuel Fortuna Cervantes. I am a student of the PhD program in Applied Science at the Universidad Autónoma de San Luis Potosí. I am going to present my research project, texture classification for object detection in aerial navigation using transfer learning and Wavelet-based filters. Well, this work is done in collaboration with Professor Marco Tulio, Marcela Mejia, and Jose Salome, and a remote collaboration with Professor Jose Martinez Carranza from INAOE. Well, I will start with a quick introduction. The use of microaerial vehicles, MAVs, has increased in engineering and civil application to explore an environment without previous information. MAVs have been used in different environments due to the air AC control and implementation of algorithms through the computer vision. In tasks of classification, detection, and location of the target, in particular in autonomous navigation, a fundamental part is that of detecting and locating target of our interest. For this reason, computer vision has become an essential analysis tool. In this work, we focus on object classification in aerial navigation tasks, where texture is involved in a physical property of the object. Okay, the approach to the problem, object detection and location is an important issue for making decisions. we know not all have been solved. In the robotics area, object detection is a problem for the robots that they perform tasks in real scenarios and in real time. Given that the lighted condition in determining orientation, object identity, shape, color, and texture. Furthermore, the information may differ in outdoor and indoor environments, which vary the target information. Then, will the task of detection becomes more robust if description capability is limited to the recognition of the texture as a physical property of the object? In recent years, math applications for object detection tasks have been studied and developed. Several approaches are using deep learning, given excellent performance in application. For example, in some tasks for autonomous navigation, we find methodology for obstacle detection in a voice using architecture called AlexNet that allows classifying the image captured by the camera on board the drone. The learning of this architecture is transferred from the ImageNet database to improve the classification performance. Moreover, to detect object autonomous landing in this world, detection system is presented to solve one of the missions, including the IMAV 2019 in the indoor competition. They involved the implementation of the SD7 on board the map. This network is used for its fast performance on low budget microcomputer with no GPU. Besides, in object detection tasks, the author proposed a deep learning approach to estimate the object center in a robust way. Also, generating a line of sight as it provides to be a solution to avoid collision with other objects. Due to complications such as varying illumination condition, object geometry, and overlapping in the image plane. On the other hand, many projects employ deep learning and Wavelet analysis in visual processing. For example, on image classification, the author mentioned that although CNN is a universal extractor, in the practice, it's not clear whether CNN can learn to perform a spectral analysis. Well, in this work, the author proposed an architecture called the texture CNN to have this approach within the CNN. The idea focused on the fact that the information extracted by convolution layer is of minor importance to the texture analysis. They use a statistical energy metric in the Fourier extraction stage. The architecture showed as improvement in performance and reduction in computational costs. In terms of the texture classification in image processing application, the author proposed an architecture called Wavelet-CNN to generalize spectral information loss in conventional CNN. This information is beneficial for texture classification as it usually contains detailed information about the object's shape. Furthermore, the model allows us to have fewer parameters than in traditional CNNs, so it's possible to train with less memory. In general, through the state-of-the-art review, we have observed that the computational intelligence algorithm improved detection strategy in micro-aerial vehicle application. This work proposes an approach based on transfer learning and Wavelet tutors. The system allowed to predict or classify the texture in image transmitted by the camera on board the drone, whose objects are in under a scenario. We used Gazebo as in virtual simulation environment. We are only interested in texture recognition, might need to know one of the characteristics of the object. So we limit the image plane to a region of the interest. As a result, the system will have the image in the RGB as well as grayscale version. These two images are the input for our proposed classification system. Next, described texture dataset was selected to be used. It contained 47 classes of 120 images in the wheel. This meant that the image had been acquired at the uncontrolled condition. This dataset includes the 10 division overlapped with 40 training images, 40 validation images, and 40 test images for each class. Our experiment will create a new dataset with the distribution of 70% for the training, 50% for validation, and the remainder, the 50% for the testing. One limitation of the dataset is the number of the image per class. So it is decided to use transfer learning method to improve the classification performance of our model. The synaptic weights are based on the ImageNet database, which will fit the first extraction state of the base architecture BG16. Before training, the hard level transfer into dimensional is applied to the one level. See figure 13. The factor of the one represents the level of the image decomposition. This new spectral information is essential for classification. Therefore, for set in the Wavelet domain, are automatically generated to determine the characteristic attributes for each texture. This information can be combined with the spatial information of the BG16 network. Also, it's essential to mention that this process is only applied to the image previously compared to grayscale, performing the decomposition for a single channel. Fine. In the first instance, the BG16 network was trained from the scratch. Result is not able to generalize it in its knowledge. Therefore, it is possible to use a transfer learning methodology. In the table 1, show the achieved performance of the pre-trained network proposed with the Wavelet filter fusion. It showed that the accuracy performance on the tree set to validate the model, training, validation, and test. In the case of the pre-trained network, sliding overfitting is observed. The model will be adjusted to learn in a specific case and will be unable to recognize a new texture. On one to improve the performance of the model is to integrate the Wavelet filters. In this case, we achieve the elimination of the fitting and we similitude between the three sets, training, validation, and test. Besides, the value of the test set is highlighted because they are images that the model has never seen. In the table 2, summarizes the achieved performance of our classification system, as well as comparison to AlexNet, training from the scratch, DCNNN, and Wavelet CNN. My model has a similar performance to the others. Okay, other metrics evaluate the performance of the DTD dataset classes. The metric shows a precision, recall, and LF1 scores are given when applying the classification report method, where it is necessary to input the true levels and the prediction level of the model. The table 2 shows that the classes that perform above 70% classification, above the precision metric. These classes are the best for 70 classes in dataset. Also, in table 4, show the 3 random classes that the performance above 50% classification in the same prediction metric. This classes selection analysis provide the basis for the design of the texture cubes of the gazebo environment. On the other hand, we can observe the correlation between classes about the test set by performing the prediction. In the figure 14, shows that the true level and the prediction level at the top of each texture. Okay, we create a virtual environment with the gazebo simulator, controlling and sending information from the camera on board the drone using the ROS framework. In the work presented in the figure 15, we positioned in a row the 10 cubes with the select texture. Therefore, the position of the cubes allow the evaluation of the prediction model during the aerial exploration. The idea of the model is to generalize the knowledge towards texture object. In total, 1,000 image captures were performed in navigation recognition for each class. In the figure 16, show that the proposed texture set, bubbly, checkered, honey, striped, and student, obtain a high correlation with their original level, about 60% accuracy. Okay, in the next figure, some images of the recognition set are shown with its original level and its prediction level. However, we can observe that the 5-stage image incorrectly predict the freely lined, polka-dotted, and zigzagged set. These 5 images related to the wall recognition set, except for fibrous, polka-dotted, and zigzagged, which achieved at least 3% accuracy. This result allowed to us a gain perspective of the generalization of the model towards texture object. Okay, I would like to show a demo with 3 objects. We can see the level and the window on the application. Here we can see the prediction inference of the model during aerial navigation. First, we take off the drone and position in the front of the texture. Second, we try to position object in the region of the interest in the image. Consequently, we will obtain the object level, and if it has probability above the 70%, it will be displayed in the drone image plane. For the checker texture prediction is okay. For the honey texture is the same, or the prediction is okay. And then the student, the 3 object, well, the student texture has a high correlation with the frequent classes. Okay. Well, frequent. Well, the student texture has a high correlation with frequent classes. I can level in the image plane. Well, okay, in the conclusion of this work, there are 3 main topics. Number 1, the location and object detection tasks using visual information and challenging, particularly when object exhibit repetitive texture. However, this tag open opportunity for various applications using micro aerial vehicles equipped with onboard cameras to be used for object detection and recognition. For instance, for parcel pickup, place recognition, and landing zone detection. Number 2, seeking to improve detection and recognition state. In this work, we have investigated the use of the spectral analysis in combination with deep neural network. In particular, in this proposal, we merge the additional create spectral furrowed maps to CNN learning. Also, it's shown that the model we use achieved to eliminate overfitting and better accuracy in the classification of texture. Number 3, the prediction model showed that the creation of the whispered understanding of the texture attached to the object. Furthermore, despite having a low classification rate, it is shown that the model correctly classifies most of the 10 of the test classes. Sorry. Okay, as the future work, this will test with other texture future, also seeking to carry out tests in real world scenarios. Well, this is my presentation.
Okay, thank you very much, Juan, for this interesting presentation. I'm very impressed always when I see algorithms for visual recognition, etc. Yeah. So I'm not expert in this field. So I don't know if the audience has a question. No. We have a question from Hugo Rodriguez. It is just an unrelated question. Do you know if Gazebo runs in Windows?
Yeah, I think that, well, it's possible. Well, I use Ubuntu, when system operating Ubuntu is, well, the word is better than Windows.
Okay. I listen that now it's possible to run Gazebo in Windows, Hugo, but I don't know exactly how do you. Sorry for the noise. Juan, for example, why, what is the interest to estimate the object texture? Because, for example, in the navigation, you have an object, the objective is to avoid. So no matter the texture, so what is the interest behind the texture classification?
Yes, thank you for your question. Well, that's interesting. Well, in the first, we want to improve the classification performance. Well, the result has to gain perspective to the generalization of the model towards the texture object. For the fusion of the transfer learning and analyzed level, well, I have more results for the using only one method.
Okay, okay. So thank you. I don't know. There are another question. Can you tell us about the computer requirements to develop this kind of algorithms?
Yes,
it's very
well,
expensive or not?
Yes, well, in my case, well, I don't have a computer with GPU. I try to use the computer with the other center in my university. Well, I have a NVIDIA card. The model was training in time for about 3 hours. Well, okay. It's necessary to the results about the training.
Okay, so maybe it's not possible to implement these algorithms on board.
Yes, it's possible. Well, I think well, I can see the application in the event. Well, it's possible. In my case, I don't have I don't have resource for the implementation. Well, I try to use environment simulation for the improve and the validate my methodology.
Okay. Thank you very much, Juan, again for this presentation, and congratulations for your work.
Yeah, you're welcome.
Okay, so thank you very much. With that, we finish this session called Autonomous Navigation 2.